Okay, so because you mentioned the prime case, I thought I would like to connect it with what I have to do. So very often we need programs for Gabor analysis where we use lattices, and the typical situation of a Gabor lattice is that we have some redundancy. I call it a redundancy factor. So if you're in a discrete case, if we have a 13-dimensional signal space, I normally would go, which is not a prime number, but a number with many divisors, and I would go for lattices which have a little bit more lattice points. But then I realized, of course, I can use my standard routine, which is generate lattices. Okay, and it's not for 13, it's for oh yeah, I see here. I can use it for other numbers. So the first command says, well, generate all lattices of size 9 by 9, or in size 9 with redundancy 9, which simply means with 9 times 1, which means 9 points. And the size of this stack of output means I can find 13 of them. So it's telling me essentially that if you take a prime power like 3 squared, you can have a little bit more. But then I took, and that's the interesting case with the plots, I took the prime number 11. And as you mentioned, I've read now these papers, or not read, I've browsed the papers of Burdas mostly, and your reports. So if I take 11, it's nice because I have 12 lattices. And I thought, well, I look at these 12 lattices. And it's quite clear that you have a horizontal subgroup and you have a vertical subgroup. Within any finite group, you have the diagonal group. So these are the pairs XX, so 1, 1, 2, 2, 3, 3. But you also have the orthogonal complement, which is exactly for me now the graph of the parity operator. I find that quite nice. So if you look at the geometry, you not only have 12 groups, but you have them pairwise orthogonal to each other. So number 1 is orthogonal to number 12. Number 2 is orthogonal to number 11, and so on. So I was checking. So it's clear each of these groups are 1-parameter groups. So it's evident in the case of lines. But even in this line, you can say, well, I can take any point because it's a prime number different from the origin, and I copy it, and whatever happens when you go down is of course coming up from the top, then you go down, and again what you come up. So essentially you see that the lines are on the one hand lines inside the phase space domain, but on the other hand they wrap around, and I'm not sure, but at some place I did, yeah, maybe I can do this here. I was doing a plot. Yeah, you see here this stack 11 is so what do we take? Maybe number 10. So lambda 10 is stack 11. So this is really a collection of 0, 1 matrices with 12, one above the other, and I choose number this, and I display just this lattice that we should see it once more. So I have to do it now. So you see, this is quite obvious, but what I find nice is I can copy it, and I can say, well, this is a tile only, and I don't know, I take a Kronecker product of this lambda with, I mean, I take 7 tiles horizontal and 7 tiles vertical, and then I think it's much nicer because it really shows you that it's the infinite lines. Only with the side effect that they are periodic with respect to the period of 11. So we could, I don't know, we could.
Is modulo 61 considered only the elementary and
it's if I say Kronecker ones, I mean that I have I put the, yeah, maybe I can do this just to show you. The Kronecker is just image Kronecker of ones 3 to make it smaller, random 5. Means that you're taking a random 5 by 5 matrix. Maybe I should also. I don't have a good separation lines here, unfortunately, but oops, there's an F missing. Yeah, so this means I take a random matrix of size 5 by 5 and make 3 tiles, because I have 3 in the form, 3 copies. You see this red object is here and here and here, 3 above each other, and it's 1, 2, 3 in this direction. So it's a 9 by 9 with 9 tiles, all of the same form. And so it's, I think, this plot above shows you that these lines are not only something like the tiles, but they are really corresponding to lines. Oh yeah, I could maybe what I could do, I'm not sure. I'm not sure. Yeah, I think I have somewhere else a plot where you can see it. So, and now the point is, for me in the group theoretical way, I was remembered of some discussion I had at the engineering department in Munich a few years ago, where they were interested in maximal number of mutually unbiased orthonormal bases. So and this is again for communication. So they want to say, well, can you have an orthonormal basis in this case with 9 elements? And then can you have another basis? And we all know that the Dirac basis and the pure frequencies are very different. So if you have something which is sparse in one basis, it's not sparse in the other basis. And then they are interested to say, well, how many such bases can you have, such that if you take an element from one basis and another element from the other basis, that their correlation is as small as possible. I think it's 1 over square root of n or something like this. And they have exactly the same picture. They say, well, you take all these maximal abelian subgroups, and it turns out, of course, if you have a prime number, any subgroup has order, I mean, trivial or order p, because we are living in the phase space with p squared elements. And so if I'm asking how many groups do we have which have order 11 in this plane, phase space of dimension 11 by 11, I'm exactly the same. And I find that very interesting. Now, the next thing is, I have just asked whether, this is not important, but the dual group is, so to say, the group. I mean, I'm looking at these functions now as functions of 2 variables, and or as indicator functions of subgroups. And for every subgroup, you have, of course, a dual group or orthogonal group. It's the group of all the frequencies, such or characters, which are trivial on the given subgroup. And so if I do all these dual subgroups, we get this list. And I think I was just comparing this collection above here. I mean, we cannot do it now quickly, but when it's printed, I think each of these groups are self-dual. So the orthogonal group is the same as the group itself. I think that's interesting. And I took out some concrete examples. I'm not sure. Yeah, I know what I wanted to do is the following. If you give me any such group, yeah, let's say you take this group here, then you would say, well, if you are getting a matrix, then you can describe it as a collection of columns. So you would say, well, one column is in the subgroup, so that's so to say 0. And then you go to the next column, and it's a coset by this side group. So of course we have 121 elements in phase space. So every subgroup has 11 side groups, cosets. And what I found interesting, so I was thinking, okay, how can I find a set of representatives or so? But it turns out, like in ordinary Euclidean geometry, you just have to take the orthogonal group. So it's quite clear. If you want to say, well, how can I fill the whole plane by filling with columns? Then you would say, well, take the original column located maybe at position 1, and then you take the orthogonal group and you say, well, this tells you have to go to the right by 1 column, 2 columns, 3 columns. So you have 11 columns, of course, all parallel to the first one. Or you can say, no, a matrix is for me a collection of row vectors. Then of course the rows have to move up and down. Now, why is this interesting? Because what I'm doing when I do this so-called spreading function of an operator, I say, oh, you're giving me a matrix, but for me, it's a collection of side diagonals. So I'm just, I realized that what I'm doing is I'm doing something parallel to this main diagonal. So I'm really saying, well, I'm doing, and I think actually what we do is an automorphism. We say, well, we have a group morphisms from this product group, which maps the main diagonal to the first row. So it's kind of moving from 11 to number 12. And the second side diagonal, which is parallel to here, of course, in a cyclic way, so the end is here, is put in the second row. And the third one is going here. And so the last entry that we would put is, of course, the lower side diagonal. And now if you just look very naively on this picture, you say, well, you can do, if you have rows and columns, you just go in the opposite direction. Why cannot we do this this orthogonal complement? And then of course you're shifting that parallel along the main diagonal. And for me, after many attempts to understand better, the Wigner business is more or less that Weyl is more or less a Cohn-Nirenberg symbol is we're playing with this group, and Weyl is and Wigner is kind of parallel to this anti-diagonal group. Now let me see. Yeah, and what I tried to see whether it's really packing. I was saying, well, what is this here? Yeah, I have two, yeah, here it's not important. I have created the stack of dual groups. So that's the D here. And I take at every level, so from number 1 to number 12, I look at the difference, and the answer is 0. So it's meaning that each of these group is self-dual in the sense of group theory. But if I take the dual group and the orthogonal group and I convolve them, which means I how to say, if you are having two, yeah, I have two sets, as I would say it this way. I have two sets of cardinality 11. And if I indicate in a discrete group, and if I indicate the, if I convolve the indicator functions, what I'm getting is, of course, there's a Dirac from here and a Dirac from here. And what I'm getting is that, the first thing is I'm asking, well, something is, no, I see, sorry. My explanation was bad. In the first list, I'm not comparing number 1 with number 1, but number 1 with number 12 and number 2 with number 11. And so what I told you, the first and the last are self orthogonal, and therefore, and I found it most interesting, number 5 and number 6, they are pairwise orthogonal to each other. The second thing was, is it true that they are the dual group, which means they have nothing in common except one element? So I'm just counting. If you take the first and the last, or the 5 and 6, or 4 and 7, and so on, and ask how many common elements they have, they are really 0. So of course, that's the situation that you expect if you have an orthogonal pair, that they intersect only at the origin. And I think later, yeah, so this is the first pair. This is the interesting pair for our discussion. Yeah, and then I was just putting something, showing you what my commands are doing. This side-digmat is the command. It's really an automorphism, moving the main diagonal to the first row. So you see here, it's 1, 7, 13. It's going to 1, 7, 13, 19, 25. The second main diagonal is 6, 12, and so on. So it's 6, 12. And if you look at it quietly, you see what's going on. Now, if you fill the first column, yeah, okay. If you fill the first column with some numbers and you apply this side-digmat, you get something which is more or less for me the indication for the flip operator, for the parity operator. So this is the anti-diagonal, but because we don't have it, the problem with MATLAB in this sense is you cannot label a coordinate 0. If you ask me, I have a 3 by 3 matrix and give me a 0, 5, you can say, well, in the first row, I put the label 0. So that's why it looks a little bit asymmetric. And yeah, this is not important. So I was doing the same thing now for 19. And I think it's pretty clear once you see this, that either they are discrete lines, exactly in the sense of orders, or they are maximal subgroups of order 19, and you have the same game, they're pairwise orthogonal to each other. Yeah, and here I tried to compute the Wigner, but that's not interesting. Yeah, maybe I should switch to the other one. Yeah, so for me, one of the things that's interesting, and maybe I'm doing it here, yeah, is I tried to first implement what's in the literature, the displacement operator and the parity operator. So for me, the displacement operator is a time frequency shift, but I have to change the phase according to the formulas that you have. So my command is very simple. I call it dispar for give me the disparity operator and the parity operator with the parameters. And now in this example, I try to make it even because I think that's more interesting. Take signal size 12, time shift, in my terminology, a time shift of 3, a frequency shift of 5. And then the displacement operator is exactly what I expect. It's a time frequency shift matrix, which is because my time shift is only 3 in the third side diagonal. And if I would plot the entries here, I would see that is a pure frequency. So I should take a larger n, then I would see a pure frequency, which has 5 oscillations over the full length. And I really took the definition now of the parity operator. So I'm saying, well, I'm taking this flip operator, which has a matrix, and I have this operator, and I conjugate the flip operator, which is kind of, for me, the anti-diagonal unit matrix, with such an operator. And I was kind of surprised to say, oh, I'm getting exactly operators which look like this, which is not surprising. I mean, I've also tested, they are really involutions. So if I apply them twice, so you're getting back. And that kind of, this simple picture brought me, oh, if you're getting building blocks which look like this, then maybe I should develop them into parallel shifts to this anti-diagonal. And so I tried to do this. And yeah, what I found most interesting is, oh yeah, that's very simple. Of course, these parity operators are in the appropriate normalization. So I think I was choosing the one in your papers. If I normalize them correctly, so I took the operator norm and divided by n, and then these numbers are equal. It's just saying it has the right norm. Yeah, here for me the par is just to show you the output. This is the parity at 0, and you can say it's the matrix for the flip operator. And I was doing some other experiments. Well, that's kind of the same thing that we had before. Yeah, here I just recall that I have now 3. Yeah, I've checked. My friend Werner Kotzek had a command that he called imp to in, which is essentially moving. This is kind of not like by Zeitigmat, but it's saying, well, if you want to make out of a column vector a diagonal matrix, so it leaves the first entry as it is. So maybe I put it here. So T5 is my T5 is my standard matrix. And if I do imp to in, no, sorry, I do something different. M5 is 1s 1 5 with once more 1 5 with 1s. Yeah. No. Yeah. Okay. So this is a matrix. No, isn't this? Yeah, this is a matrix which is constant along rows, but that's not what I want. Sorry, I was doing a stupid thing. I should take a 0 matrix of size 5 and put into the first column the numbers 1 to 5. So then I have just in the first column, so that you see where the numbers are. And I do the imp to in of this matrix. Just it shows you that it's moving every vector from the first column to the position in the diagonal. So and I have essentially checked some invariance properties. So we have now some automorphisms of the group, and we have a Fourier transform in the 2-dimensional sense, and we even have a symplectic Fourier transform. And what I'm doing here is to quickly check whether the symplectic Fourier transform is compatible with the automorphism. And yeah, so the 2-dimensional Fourier transform is not compatible. It says the difference, they are different. The symplectic Fourier transform, however, is compatible with this transformation. So you can have an automorphism. And here, yeah, so imp to in is nicely compatible with the symplectic Fourier transform, which is important between Kohn-Nirenberg symbol and spreading function in my terminology. And I think in your case, it's Weyl to Wigner or so. I'm not sure, I've not checked it. And the Zeitigmat, I need 2 routines. One is either Zeitigmat first and then 2-dimensional Fourier transform. Then I can do it in the opposite order. If Fourier transform first and then the other one. Or I do it the Zeit2mat first and do this. And actually, I can also confirm once more that if you have some test matrix and then you do them in the opposite order, Zeitigmat of Zeit2mat of T5, that should be okay. And also the opposite thing, T5 should be the same as Zeit2mat of Zeitigmat of T5. I'm not sure if that works now, but let me try to see it. Yeah, so you see that they're identical. Yeah, so this is more or less just a confirmation that I have now more or less. Yeah, well, I have also implemented the inverse automorphism for the imp to in. I called it, of course, in to imp. I have not used it really much. So we have different automorphisms of phase space. And what I also have tried, that's something I would like to mention. If I take in the other plot, if I take the easy, no, that's the wrong one, this one. If I take the original plot with these 12 lattices. So I was saying, well, now we have, I think I was trying the imp to in. So you take this, and from the first application, I get number 11 and so on. So, and of course, if you do an automorphism on a group and there are only finitely many subgroups, after a while, I will come back. And what I found extremely interesting, I think, I'm not sure, but I remember that in this case, I was getting 12 lattices, 12 different lattices. So I applied this automorphism, alpha squared, alpha to the power 9, and then alpha to the power 10 was giving me the identity operator. So then you're asking, well, if I start with this one, which one will I get? And I was getting exactly number 1, if I remember correctly, number 1, 2, 3, 4, 5. Sorry, I should have said 6 and 7. So 6 and 7 did not appear, and or I don't know, 5 and this. So 2 of them in the middle row did not appear, and I have no argument why this is, but it seems it's interesting. I mean, any finite group applied to any automorphism applied to a finite group has a cyclic length, so you will get different subgroups up to some order. I found that interesting. And now maybe, yeah, what I was trying to do here is, what was this? Yeah, here I was trying to take, I think I was trying to do the, yeah, I forgot what I was, yeah, here, oh, yeah, here I was doing, what I was doing here is the following. I was doing a random, yeah, so kind of each point, so you give me a lattice now, and then I would say, okay, it's nice because these lattices are commutative lattices. So if you're taking any linear combination of those 9 time frequency shifts, so once more, we're in this situation, no, not 9, 12. Yeah, 9, sorry, I start once more. The prime number was 11. We have 11 plus 1 is 12 subgroups. And they are nice in the sense that they are commutative subgroups. So if you take any point and turn it into a displacement operator, the corresponding 11 displacement operators will be commutative. So they will, I mean, if you take anything like this, the powers are only changing up to phase factors, and the phase factors are numbers and they commute. So whereas general time frequency operators do not commute, if you take only any 11 out of any one of these lattices. So you fix the lattice and then you do a linear combination. And why I'm doing this, because I wanted to find the common, a typical common eigenvector. So what would you do if you do this? I would create a general translation operator from this. So a linear combination of shift operators would mean I would generate a random convolution operator, and you would of course get the pure frequencies as the eigenvectors. If you would take a random linear combination in this case, you would say, oh yes, you have a multiplication operator with this pure frequency with another pure frequency, and you would get a random multiplication operator. What is the eigenvalues? These are the unit vectors. So you would have, here you get the Fourier basis, here you get the Dirac basis. Now, what happens, what is the shape of the eigenvectors that we have here? And I'm looking at these things. So you have movements in a particular direction. And so I was not surprised, or I had done such things earlier systematically with a different motivation. So if you're asking me, how does the what is the spectrogram of a pure frequency? Because this is an eigenvector for the translation operators, and it's of course a line, a horizontal line. what is of a Dirac at any position? Well, it's a vertical line, and not surprisingly parallel to the orientation of your lattice. And it should not, I mean, the n is so small that it doesn't look very nice. So we could do something similar for larger n, and then you would see nice straight lines. So I'm quite sure that, yeah, I mean, at that time I was interested in chirp signals, so the generalization of the e to the ix squared. And so these are clearly signals which, yeah, okay, maybe the most interesting thing are maybe number 2 and number 11. So this would be something, yeah, so these are chirps which have only 2 side diagonals, or they're, yeah, kind of, if you repeat this, yeah, maybe we should repeat this then, because you should see that the position of these lines may change. So I'm just doing the same thing. You see here, this horizontal line I was picking, I mean, this is a random experiment. I'm building a small 11 by 11 matrix, which is unitary. And therefore, MATLAB is computing the eigenvalues and is giving you some eigenvalues, but there's no natural order because unitary matrices have complex eigenvalues. So I think MATLAB is choosing someone. So you see here, this has changed. Also, this line, the orientation is the same as before. Also here, it's the same as the corresponding lattice. And I think that, so you see here, the orientation is this. Maybe we focus on maybe the first one, the second row. It's very steep, and it should be the same here. Yeah, so maybe it's so steep that it's not nicely plotted or so. And let me see, I think that's all. So what I finally did is, yeah, one more thing is, what I have to see. Yeah, I was trying to, I was doing a Weyl-Wigner routine, which is computing really strictly according to, I mean, that's why it's very slow, but for small n, it's doable. I was really saying, well, I can build the matrices, I can take the trace of the given matrix with respect to the system of displacement operators or with respect to the parity operators. And so I think what I get, the interesting part should be this one. Here, to get a little bit closer to the continuous case, but still with some small number, because I have to do n squared traces, so I have to build n square matrices, blah blah blah. So the Weyl symbol is quite nice. That's fine. And the Wigner, so sorry, what it is? This is a Gauss function, so it's a discrete Gauss function of length 72. And of course, it's now on purpose, I choose an even number. And this 72, and that's the Wigner. And of course, it looks periodic, and of course it is periodic, because that's another series of small experiments which I did, is the number of displacement operators that you get because you have this doubling of time and frequency shifts is exactly a quarter of all the possible, I mean, the dimension of the orthonormal basis of the displacement operators that you compute for even numbers is exactly a quarter from all the possible of the number of the dimension of the n squared. So yeah, so once more, I'm saying whatever displacement operator you take to create a parity operator, you can shift the displacement parameters by half the signal length. So in this case, I could take plus 36 in either time or frequency or both or none. That gives me 4 possibility. And in each case, I would get the same parity operator. So you could argue that in a way, why did I compute these 72 squared elements? Because I could done it on paper and verify that a quarter of this graph is already enough, and then I copy it and make 4 tiles of half the size. That would be a possibility or so. And then I was also checking, that's not mature, the site, the marginal properties. Where is it? Yeah, what I found interesting is that I thought, well, for me to understand, well, any operator, I always look, among others, on the spreading function. So I'm going from the original operator to the spreading function. So kind of we have two things. We have seen that, roughly speaking, the parity operator as matrices are concentrated on a cyclic antidiagonal. So they have a very nice, simple structure. But if I take them on the, where is it? Yeah, here. If I look at the spreading domain, and what I'm displaying here is just where do I find non-zero entries? And then you see, you have to look closer here, the labels here. The labels are 0, 2, 4, and plus, minus, or so. So I do this display in a centered way, but it just tells you I'm getting only even numbers of displacement, which you will not find surprising because multiples of 0, 1, 2, 3, 4, 5 by 2 are 2, 0, 2, minus 2, plus 4, and so on. So it means if I would take, and I've not finished this, if I would take a random matrix at these positions, you would tell me that I get a collection of matrices of dimension n squared over 4. I get exactly as many, I mean, the dimension of the space of those matrices at the spreading domain is exactly the dimension of those spent by the parity operators. And I'm quite sure, I have not tested it finally, that these matrices are exactly the ones that you get as a linear span of the parity operators according to your formulas if you take an even number. So once more, you say we should avoid, or it's plausible, one should avoid even signal lengths, because then we don't have enough displacement operators according to the usual rule. And my expectation is that while we get exactly, we can, in a different representation, we can describe them as the ones which have non-zero entries only at 1 out of 4 sampling values. So we could have some value at this position here and here, but only if the values are here, we can do it. I have probably, that would not be too difficult to make an experiment to verify it. But what I realized then is, if I take this other picture of these antidiagonals, so why don't I take the parity operator, and instead of conjugating it with the displacement operators, I try to move them up and down. So I have a routine, I'm not sure, yeah. I have made a routine which essentially imitates this movement along the main diagonal. So moving this antidiagonal up and down. And of course, what was interesting is that the moving up and down is more or less the conjugation with the shift parameter. So I'm still thinking, well, you give me a displacement operator, but I disassemble it, and I take the shift parameter to move things up and down, and then I multiply with the frequency parameter, but I'm not conjugating, because I think this kills some of the entries. So I will send you this, but essentially this is the routine that came out of this inspection. And then I made my routine, which I call MAT to Wigner, which is kind of my Wigner now, and Wigner to MAT. And this is a unitary mapping. Yeah, maybe I'm taking XX random CN, and I'm not sure what is the N. Yeah, okay, it doesn't matter. And VXX is Wigner. No, take this operator, this matrix, to the Wigner with this understanding. So decomposing it in side diagonals and taking a Fourier coefficient, the Fourier coefficients of these anti-side diagonals. So that's just done quickly. And I look at the, yeah, maybe I'm looking at the Frobenius norm is just the sum of the Euclidean norm of these n squared pixels. And if I do the same thing for the Wigner, oh yeah, okay, I see what's going on. It's normalized such that it's 1 if I divide by square root of 12. So yeah, this has to do because kind of the Fourier transform is along the antidiagonals and they have lengths n, and therefore, and what I found, which took me quite a while, is that if I show you the code, or maybe I type much too big here, if I show you the code, yeah, my first understanding was, can I do something symmetric to the main diagonal, which is what I understand, parallel with decompositions parallel to the antidiagonal, hoping that in this way I would get something which is good and invertible or so. And I realized after, well, looking at small examples, and that's not by verifying formulas, that's maybe something where you're much better or so. But then I realized, oh, it looks, it's not the spreading function of the operator or so, or something like this, but if I flip in a vertical way, so I have to show you this, T5 is my test matrix of size 5, and flip vertical of T5 just means I'm doing an involution column-wise. So I'm reading, thinking that the values 1, 2, 3, 4, 5 are the unit roots of order 5. I'm reading it backwards. So you're still starting with omega to the power 0. So 1 is here, but then you're going in the opposite direction. So, and the point is, my routine, so here it's a 2-line argument. The code says, well, you're giving me a square matrix. I need only the size of the matrix n. And then I flip the matrix so that I keep the first row, and I switch the order of row number 2 is the last row, 3 is the second last, and switch in this way. And then I apply my smart to spreading routine. That turned out to be the very quick and very efficient way to do it. And if you just want to see the code which is doing the inverse, type, what is it? This, well, I call it Wigner, and maybe it's not justified. Then, of course, I'm doing exactly the opposite. Instead of multiplying with m, I'm doing the division by n. Then I do the opposite of from matrix to spreading function, which is called spreading back to the matrix. And then the opposite of flipping vertical is, of course, flipping once more vertical. So this is also extremely quick. And because the flip is self-inverse and spread to mat and mat to spread are self-inverse. And if you look at the code, that it means, oh yes, one is saying put the side diagonals to row vectors, and the other is saying, well, put row vectors back to diagonal vectors. And my friend is doing put column vectors to row vectors. So I think one can combine this. So the point is, these are very efficient. And the last thing, I'm not sure if I have this prepared. Yeah, no, maybe that's not interesting. Yeah, here I was playing around, picking out the side diagonals or so. Now, what I was doing is, yeah, maybe, yeah, maybe I stop here. Stop share, where is it? Oh, cannot find my command window.